This is a 2009 paper, the start of the electric power section. The first question is about generators or alternators. So even though this looks like a motor, it can be a motor. When we spin it by hand, it generates electricity. If we put electricity in, it would make us a motor. So we're talking about spinning this by hand because we're talking about generators and alternators. The difference between them is one's DC and one's AC. And the first question is indicate whether this device is a DC generator or an AC alternator. The difference between the two is either one's going to have slip rings and the other will have a commutator. And what have we got here? These guys are slip rings. So that's our first answer. Because of the slip rings, this is an AC alternator. Alright, the next question. The coil has a single loop. Single, so that means N equals 1, of area this, and it can be rotated about its axis in a uniform magnetic field. Question 2 is asking us, what tells us the maximum flux that can go through the coil, flux, equals that. What's the magnitude of the magnetic field? This is a flux question, but they're asking us the field, not the flux. So we have to find this guy, so we have to rearrange. So if we divide both sides by A, we get B equals flux over area. The flux we've got here, 7.2, 10 to the minus 6. Area is 9.10 minus 4. When you do that calculation, you get 8 by 10 to the minus 3 Tesla. An interval of 0.02 seconds, this is the time. The coil is rotated by 1/4 of a turn from the rotations shown in figure 1. So a quarter of a turn means it goes from, I can't remember how it was in figure 1, let's just have a quick look. Here it is there. That's the wrong question. Oh, yeah. In figure 1, when it's completely flat, there's no flux going through it. And then if you do it a quarter of a turn, here's my picture of it being done a quarter of a turn, there's the full amount of flux. And we know that full amount of flux as I've given it to us here. This is the maximum flux here. So this is flux equals 7.2 by 10 to the minus 6. So the change in flux for this quarter turn equals final minus initial, which is pretty easy because that's 0, so it's 7.2 by 10 to the minus 6. And we know the time it takes to go and change the flux by that much. We know the time it takes is 0.02. We don't have to times this by 4 or anything like that because it's only a quarter of a turn. We're going from 0 flux to full flux in a quarter of a turn, and they're giving us the time for a quarter of a turn. So these are the values that we use. So the actual calculation, EMF equals negative N, change in flux over change in time, is 1 for there's only one coil of it. I'm not going to worry about the negative. We'll leave that out. That ends up telling us which direction the current flows in, but we're just going to leave that for now. The change in flux is 7.2, 10 to the minus 6. The time is 0.02. We'll do this on our calculator. and I get 3.6 by 10 to the minus 4 volts, which is a small voltage. The reason it's such a small voltage is because we've only got one coil, one loop. To make much more voltage, like in a power station, usually they have lots and lots of loops, and you have the voltage increases due to that.